11.2, finding limits using properties of limits. So we looked at limits graphically in 11.1, and now we're going to look at being able to find them algebraically, because drawing a graph is not going to be the fastest way to do things most of the time. So with our first three, we're looking at some limits that are pretty straightforward. And if you do look in your textbook, you're going to find all these different properties that they want you to use. We're just going to kind of cut to the common sense approach. So if you are looking in your textbook, like we in 11.2, we're skipping most of the stuff that they're doing. We're just kind of going to the end of that section. So I should know from 11.1 that when I am finding the limit as x goes to 3 of 5x, most of the time it's really just the same thing as plugging in 3 for x and finding my y. So if I am able to just directly substitute and get an answer, I am allowed to do that. So in this case, I would do 5 times 3 and get 15, and that is going to be my limit. And I know that when I graph 5x, that would just have been a straight line. I would be figuring out where x is 3 on my graph and what my corresponding y value is. So sometimes a limit is just the same thing as substituting. And the second one, I have the limit of a constant. So this would be like the limit of the function y equals 3 or f of x equals 3. And I want to know what happens when x is 2. Well, y is always 3, so I'm just going to write down that it equals 3. So this is kind of a tricky one for some people. On the last one, we want to know what happens when limit as x goes to 1 of this function. So I'm going to directly substitute 1. So if we can just substitute, we should substitute directly. So that is our first option that we want to use, is to substitute directly. And it won't always work, but sometimes it works. And when it does work, it's really easy. So remember, a limit, it's like as x goes to 1 or if x just equals 1, right? We just have to be close, but sometimes it's actually going to be equal. So 4 plus 2 is 6 minus 6 plus 5, so just the limit's going to be equal to 5. So these are the first problem type where you're just going to substitute directly. Sometimes that doesn't work. So if I am looking at these next two, and the first one says limit as x goes to 3, if I put a 3 in my denominator, I have something that's undefined. So this is kind of like some of the stuff that we graphed in 11.1. And if my denominator is a problem, there's different strategies I can try. One of them is to factor and see what happens. So let's go ahead and factor our numerator. And it turns out that numerator and denominator have a factor of x minus 3. So we can cancel or just divide that out. And we end up with the limit as x goes to 3 of the simplified function, which is x plus 2. So this means if I'm graphing, remember this is like when we graph, just trying to connect it with what we did yesterday, we'd have a graph of y equals x plus 2, but we'd have a hole at 3. But when we're doing limits, we don't really care that there's a hole, do we? With a limit, it's just got to be close. So I'm going to only work with x plus 2 here, and I'm going to substitute 3 in now for my x, and 3 plus 2 would be 5. So my limit of x plus 2 as x goes to 3 is just going to be 5. So on the next one, I can tell that I cannot directly substitute again. 2 minus 2 would be bad for the denominator. It doesn't work, but you always try that first, right? We always want to directly substitute. And if it was limit as x goes to 1, then we'd be able to go ahead and do that. And looking at my numerator, I also see that I cannot factor this because there's 5 terms. So my factor by grouping, I can't do. I'm not really sure where to go with this. But it could be that the numerator is still something times x minus 2, right? X minus 2 might be a factor. And so a way that I can always figure that out is with synthetic. So I am going to divide my numerator by x minus 2. So I'm going to use a positive 2 here, and then my coefficients would be 1, negative 2, 1, negative 3, 2. And then we'll go through and do our synthetic. I'll bring the 1 down. 1 times 2 is 2. Add, I get 0. Multiply, 0. Add is 1. Multiply is 2. Negative 1, negative 2, 0. So it turns out it was a factor. X minus 2 is a factor. And I am left with let's see, I am left with, because I started out with x to the fourth, this is going to be an x cubed. I have a 0x squared, I have some x, and I have a constant. So the way I would write this then, in the numerator, I could have x minus 2 minus 1x cubed plus 0x squared plus 1x minus 1. So let's just call that x cubed plus x. Oops, I said cubed, but I wrote squared. X cubed plus x minus 1 all over x minus 2. And so again, my x minus 2's cancel out. So that would be a hole on my graph. But when I am finding a limit, I don't care that there's a hole there. A limit has just got to be close. So x cubed plus x minus 1, and then I'm going to go ahead and substitute 2. So let's see, 8 plus 2, 10 minus 1 should be 9. So my limit is going to equal 9. So our first strategy was to directly substitute. Our second strategy is to factor and simplify. So if you have an issue with your denominator, you could always try factoring. So that's one way. So my next strategy is going to involve when there is a square root. So it turns out on this one, when I have x goes to 0, remember I'm always checking that, 0 does not work in my denominator. I can't divide by 0, so I've got to have a different method. And so one thing that I can do is I can rationalize. And in this case, my denominator has already been rationalized. I don't have any square roots in my denominator, but I could choose to instead rationalize my numerator. So I would rationalize by multiplying by the conjugate. I have a square root minus 2, so I'm going to multiply by that same square root plus 2. So here's my original problem, and now I'm going to multiply it by square root of 4 plus x plus 2 on the top and bottom. And this doesn't always work. Sometimes you don't even have a limit. We'll look at that in 11.3. So in my numerator, when I'm multiplying, and they both have the square root of 4 plus x, and then there's a minus, and then there's a plus, and there's 2's. Remember, we get that difference of squares. So I'm going to have the square root of 4 plus x, and I did not write 4 plus x. The square root of 4 plus x, I'll have that squared, and then minus, and then 2 squared. So that's how difference of squares works. In my denominator, I'll have x times square root of 4 plus x plus 2. And this is still a problem, right? If I put a 0 in here, I'd be multiplied by everything. So what I'm really hoping is that that factor of x gets canceled out. And so I'm just going to let it hang out there. I'm not going to distribute it or anything. I'm just going to see what happens in the numerator. So when I take 4 plus x and I square it, I square the square root, I just get the 4 plus x. And then minus 2 squared would be minus 4. So it turns out that these 4's, 4 minus 4 would be a 0. So now I have x over x. Oh, see, that x is gonna, we can cancel it out. That's looking good. So now I would have 1 over the square root of 4 plus x plus 2. And now at this point, if I put 0 in my denominator, it's not going to create any more issues. So now I can find my limit. So let's put 1 over square root of 4 plus 0 plus 2. So 1 over the square root of 4 plus 2. So 1 over 2 plus 2. So 1/4. So our limit is going to be 1/4. All right, so let's write down, did we write down strategy 3? We did. We wrote down rationalize. Okay, so last problem and last strategy we're going to illustrate right now is this complicated like fraction and a fraction stuff. So our fourth strategy is going to be to just do the math and simplify. Do the math. So let's put all these fractions together and just see what happens. So we're just going to go through and simplify. So right now, as x goes to 0, that would give me a 0 in the denominator. So I still am always kind of checking that to make sure that direct substitution is not an option. That's always our first hope. And so that means I'm going to have to go ahead and do the math and simplify this. So I'm going to take my numerator first and put it together in one fraction. So I would multiply the first one by 5 over 5, the second one by x plus 5 over x plus 5. So that means 5 times 1, that'll be a 5. I got a minus sign. 1 times x plus 5 is just x plus 5. And then all over that little denominator, that common denominator now is 5 times x plus 5. And then I have my giant fraction, right? That's this one right here, this fraction bar. It's all over x. And if I'm dividing by x, I'm really multiplying by the reciprocal. So we'll have to do that in a second. So let's see, 5 minus x minus 5. I want to distribute my minus sign over 5 times x plus 5. Okay, so now I have a negative x over a 5 times x plus 5 all over x. So I need to extend my page here. And remember, I said that dividing by that x was going to be like multiplying by the reciprocal. So I'm going to go ahead and do that. Negative x over 5 times x plus 5 times a 1 over x. So that means in my denominator, oh, look, the x's are actually just going to cancel. I don't even have to go ahead and multiply it. So I will have negative 1 over 5 times x plus 5. Okay, and now I cannot even remember what number we were looking for our limit. So our limit was as x goes to 0. So now I can go ahead and I can find that. So limit as x goes to 0. So negative 1 over 5 times 0 plus 5. 0 plus 5 is 5. 5 times 5 is negative 1 over 25. So just to quickly review strategies and to add one more. So our strategies are to first just substitute. And then we looked at, well, sometimes you have to factor and you can cancel some stuff out. We looked at rationalizing. And we had to rationalize the numerator. So that is an option, just like you would a denominator. We even looked at simplifying, where we did the math and we put the fractions together. And the last strategy, the one that we really don't want to use, but sometimes we do have to use, is just making a table. And so if I was making a table, say I was doing the limit as, let's say limit as x goes to 4 of f of x, then what I would do is I would make an xy table and I would come up with numbers that were closer and closer to 4, right? I might start with 3 and then 3.5 and then 3.9 and 3.99. And I'm trying to see what happens when x is 4. And then maybe I look at 4.01 or 4.1 or 4.5. So that's how we'd be making a table. And we'd find all those different y values. So we looked at tables a little bit in 11.1. I think there's a couple homework problems that had tables, but that's really our last ditch effort. We don't want to make a table. So these again are our strategies for finding limits.